Okay, good. All right. So I want to start reminding everyone what it is we're talking about. So in matrix multiplication, I give you two matrices. These are n by n matrices over the complex numbers, and I want you to compute their product. And I want to understand how easy or difficult it is to compute this product. And for this talk, our measure of complexity is going to be the number of arithmetic operations we need, right? The number of additions and multiplications of complex numbers. We're going to ignore bit complexity. Now, the complexity of matrix multiplication is typically denoted by omega, the exponent of matrix multiplication, which is just the smallest real number, so that for any positive epsilon, you can multiply two n by n matrices and n to the omega plus epsilon many operations. So what do we know so far about omega and the complexity of matrix multiplication? Well, from the definition, we know this exponent is somewhere between 2 and 3. And in an influential work from 50 years ago, Strawson showed that, in fact, omega is strictly less than 3. And since then, there's been a long line of work, most of which is not on this slide, showing that we can improve the upper bound on omega. And in particular, the most recent published upper bound is this one due to Allman and Vasilevska-Williams from about 2 years ago. But this slide is actually out of date as of like late October, because there was even further progress posted on arXiv by Duan, Wu, and Zhou, improving the exponent in the third decimal point. So we have a lot of work that goes into these fast algorithms for matrix product. And of course, matrix multiplication, it's this fundamental problem. We'd like to get really fast algorithms for it. But why should we care? What does this buy us beyond just multiplication of matrices? Well, it turns out this problem is really, really useful if you want to do other things. For example, if you want to compute the determinant of a matrix, you can do this quickly using fast matrix multiplication. More generally, you can compute the characteristic polynomial of a matrix. You could factor that matrix. You could solve a linear system. Basically, if you want to do fast linear algebra, it's enough to just get fast matrix multiplication. But you can also use matrix multiplication for problems that don't look like linear algebra, at least on their face. So for example, if you want to detect k-cliques in a graph, if you want to recognize strings from a context-free language, you can do this quickly using matrix multiplication. And if you've thought about these problems before, you know that there's a matrix sitting around somewhere in these problems, but I mean, the first one looks like a graph. The second one looks like just a grammar. It's not obvious where the matrix might be. And just to drive home the point that this is a really useful, widely applicable problem, this paper by Allman and Vasilevska-Williams, I looked on Google Scholar, it's been cited about 200 times in the past 2 years, which is like incredible for a theoretical computer. If omega is 2, if we get these really fast algebra product for linear algebra, for all kinds of problems, and we live in an absolutely wonderful, beautiful world, but maybe that's not the case. Progress on upper bounds is slowing, and in fact, we have some known barriers for the current techniques we have. So what if omega happens to be larger than 2, right? That says matrix product, linear algebra, all these other problems, like they take some mild amount of work to solve them. Can we use this to somehow design algorithms in an interesting way? And the point that I want you to take away from this talk is that yes, we actually can use lower bounds on omega to design algorithms. And if you are thinking about, okay, what algorithm could we possibly get from this? Well, it kind of gives it away. We're going to talk about polynomial identity testing. So before I tell you the main result, I want to take some time just to recall polynomial identity testing. What is the problem? What do we know about it? Why do we care? So polynomial identity testing is a lovely problem where as input, I give you a multivariate polynomial. And I want you to tell me, is this polynomial 0 or non-zero? Now, how am I giving you this polynomial? If I give it to you as a list of coefficients, of course, this is easy. Right? You just check if every coefficient is 0 or non-zero. But in this instance, I want to give it to you in a slightly more compressed format. I'll give you an algebraic circuit that computes the polynomial. Right? Now, this is a succinct representation. You can do something with this. You can evaluate the polynomial given the circuit. Right? The circuit is an algorithm to evaluate this polynomial. But it's too expensive to expand this polynomial as a sum of monomials, right? So there is something we can do, but it's not obvious how to actually test if the circuit computes the 0 or non-zero polynomial. Now, if you haven't seen this before, let me give you an example of one instance of PIT. So here I have a matrix. It's a 5 by 5 matrix of variables. I zeroed out some of the variables. I left 10 of them alive. And I want to know, is its determinant 0 or non-zero? And you can sit and stare at this for a while and find out that the determinant is non-zero, and I've highlighted a monomial that's going to survive when you expand it. Okay, that's great, but why should you care if some matrix I pulled out of the air has a non-zero or zero determinant? Here's a different question. Here's a bipartite graph. Does it contain a perfect matching? And again, you can look at this graph for a while and find out that there is a perfect matching in this graph. Here's one of them. And of course, I'm asking you these questions on the same slide because these answers are correlated. The reason this determinant is non-zero is exactly because this graph has a perfect matching. And in general, there's a way to take a bipartite graph. Determinant encodes whether or not there's a perfect matching present in that graph. So this gives us our first application of PIT, which is algorithms for perfect matching. And in fact, these are parallel algorithms for perfect matching, because you can compute the determinant efficiently in parallel, and you can solve PIT in parallel, randomness. So it's not a deterministic algorithm, but it is, it is a parallel algorithm, which seems like a very nice thing. What else can we do with PIT? Well, the AKS primality test is based on derandomizing a particular instance of polynomial identity testing. So you can test primality of integers. You can also factor algebraic circuits. You can test if one circuit divides another. You can also solve other problems. Well, okay, so polynomial identity testing also appears in the proof of IP equals P space. And you can solve other problems like testing equivalence of so-called read-once branching programs. And if you don't know what these are, this is just some non-uniform model of computation for Boolean functions. And the point is, if I give you two of these read-once branching programs and I ask you, do they compute the same function, you can actually solve that using PIT. So this is a useful problem. It helps us solve things that don't necessarily look like algebra. So what do we know about solving PIT? Well, we know there's a randomized algorithm. And in fact, there's a randomized algorithm with one-sided error. And it's very simple. You pick a random point, evaluate at that point, and then you say that the polynomial is 0 exactly when you get a 0 evaluation back. Now, if you want to de-randomize this algorithm, it takes exponential time. You need to evaluate this polynomial at an exponential number of points. And you might ask, well, we have a fast randomized algorithm. Can we get a fast deterministic algorithm for PIT? And this is a question that's been studied for quite some time. And we know there are intimate connections between de-randomizing PIT and proving circuit lower bounds for algebraic circuits. In one direction, we know that lower bounds for explicit polynomials like the permanent can be used to de-randomize PIT. And in the other direction, we know that if you can de-randomize PIT, then you can use that to prove new circuit lower bounds beyond the state of the art. So there's a connection between circuit lower bounds and de-randomizing PIT. And I told you we're going to look at a connection between matrix multiplication and de-randomizing PIT. Now, maybe this isn't so surprising in the sense that a lower bound on omega is a circuit lower bound, but we'll get to why these results don't necessarily imply the main result of this work. But now with all that background established, let me tell you the main result from this work. I'm going to say it in two different ways. And I first want to tell you this result as a sort of win-win kind of theorem. Okay, so we have two options, at least one of them is going to be true. First is maybe omega is 2. And if omega is 2, we've done a great job. We have these really fast algorithms, we can all pack up and go home for the day. If omega is not 2, we get some interesting de-randomization of PIT, so that if I want to test a circuit of size n to the 1 plus delta, I can do this deterministically in time exponential in n to the 1 minus epsilon. Okay, so I'm testing a circuit of size slightly more than linear in time slightly sub-exponential. And just to set expectations, the naive, straightforward second item here is going to run in time exponential in n log n. Okay, so we're saving a small factor of n in the exponent. Now we think, it's popularly that true, in fact, that something much stronger than the second item is true. And this says at least one of these is true, but of course we don't know which. And we think both are. Now that's this result as a sort of win-win statement. Let me tell you now as a sort of hardness into pseudo-randomness version of this theorem. Okay, so I'm going to restate this. So suppose we have a lower bound on omega. We're going to use that to design some algorithm for PIT. And the algorithm we get, it's going to take a size S circuit as input, and it's going to test if that circuit computes the zero polynomial or a non-zero polynomial. And it's going to do this deterministically in time exponential in the square root of n times s to the 1 over omega times log n, and then we pick up an extra s factor on the outside there. Now, if you think about it, when you prove a stronger lower bound on omega, you're proving an upper bound on running time of this algorithm. One setting of parameters just to get a feel for what can we really get out of this, how much juice is there to squeeze. If, for example, someone says tomorrow, hey, omega is 2.03, and I want to test a circuit of size n to the 1.01, right? So just a little bit more than linear, and we have some kind of lower bound on omega. This algorithm will run in time exponential in n to the 0.998. Okay, so I mean, it's the naive thing would be like n log n in the exponent, and you get an n to the 998. Right, so you're saving a small factor of n in the exponent. And now you might say to yourself, well, wait a second, I really believe that omega is 2. And you're saying if omega is not 2, then you can prove a theorem. Of course, false implies true, so what's going on? There's a more fine-grained version of this that gives you an interesting algorithm, even if omega is 2. All right, going to see R inverse. So what's this R underlying function? It's the border rank of matrix multiplication. Now, if you don't know what the border rank of matrix multiplication is, you should think of it as the number of non-scalar multiplications you need to compute the product of two n by n matrices. Okay. So for example, if you remember Straussen's algorithm, Straussen shows how to multiply 2 by 2 matrices with 7 multiplications. So that says the border rank of 2 by 2 matrix multiplication is at most 7 instead of the trivial bound of 8. So how does this relate?
Before we go to the question in the chat.
Yeah.
So the question is, can we understand the result as if we have a lower bound on computing the determinant instead of the permanent? Then we have a better deterministic algorithm for PIT.
In some sense, yes. Yes, and we'll develop that idea later on in the talk, but that's more or less the idea, yes. Yes, okay. Right, okay. So how does border rank relate to omega? If you haven't seen this before, you can alternately define omega in terms of the border rank. And the way you do this is you take border rank, you take its logarithm base n, and you take the limit as n becomes large. Now, why am I making a point of talking about border rank here? It's that this is a finer grained notion of the complexity of the matrix product. So it could entirely be the case that omega is 2, but the border rank is like n squared times some large polylogarithmic factor. And if that's the case, then we still get an interesting algorithm for PIT, even if omega is 2. This could test, for example, if this were true, we could test circuits of quasi-linear size in some non-trivial amount of time. Okay, so that's the statement of the result. So now I want to tell you how we're going to prove this result and how we're going to design our algorithm for PIT. Okay, and the object that we're going to try and construct here is a hitting set generator, which is kind of analogous to pseudorandom generators that you may have seen in Boolean pseudorandomness. So our setup is we have a set of polynomials, curly C, that we want to hit. We want to test these polynomials. And we're going to build a generator. It's going to be an object that reduces the number of variables present in these polynomials. Okay, so what's a hitting set generator? It's a map that will take L variables to N variables. And the coordinates, the output coordinates of this map are given by polynomial functions in the inputs. And we're going to say it's a hitting set generator for this class. If for every polynomial in the class, that polynomial f is 0, if and only if its composition with the generator is 0. So you should think of this as a way to reduce the number of variables present in your polynomial while preserving zeroness and non-zeroness. Right? Clearly, zeroness will be preserved. Preserving non-zeroness is the interesting part. Okay, and there are two parameters that we're going to look at in this generator. One is the seed length, which is the number of input variables. And the other is the degree, which is just you take all the output coordinates. These are all polynomials. They have a degree. You take the maximum of these degrees. Do them for PIT. Well, let's think about this. So if I have a polynomial f that I want to test, and I have a generator, there are two algorithms that I could run. The first is I take f and I test it by brute force. And if I do this brute force test, how many evaluations I need? I need +1 to the n many evaluations. Now I have this generator sitting around. What can I do with that? Well, I could test the composition of f with g instead. And if I do that, the number of evaluations that I need drops to something like the product of the degrees +1, seed length of the generator. What you should see is the dependence here on the number of variables is really, really bad, right? We get this exponential dependence on the number of variables, but only some polynomial dependence on the degrees. So if I can design a generator, relatively small degree, but small number of variables compared to n, then we're in business. Then we're going to get a nice deterministic algorithm. So for the rest of this talk, I'm going to focus exclusively on constructing this generator. And now we all know, we're all experts on how to turn that into an algorithm for PIT. Okay. So what are we going to do here? We're going to do a kind of hardness versus randomness, but in a white box sense. And what do I mean by this? Well, the existing line of work on hardness versus randomness in the algebraic setting, take a circuit lower bound and turn it into a hitting set generator. But the problem is that conversion usually incurs some kind of large polynomial overhead, at least a cubic overhead, in the construction. And here we're in a really tight regime where we don't want to lose anything. If omega is, say, 2.1, that's a lower bound of n to the 2.1 on a problem with n to the 2 inputs, right? That's just barely above linear for the lower bound. So we can't afford a large polynomial overhead. So what we'll do instead is we know our hard polynomial, we know its matrix multiplication. Let's do something with that. And the intuition here is that, well, if omega is large, and say 2.1, this could be any value larger than 2, but just for the sake of making things concrete, we'll use 2.1. If omega is 2.1, then that says circuits of linear size, they shouldn't be able to do linear algebra, right? That should take some amount of work. And if they can't do linear algebra, well, our idea is let's design a generator where breaking the generator requires you to do some kind of linear algebra. Okay, this is the idea. Now we'll make this precise in a moment, but you should really keep this, this is the takeaway, like maybe philosophical message that if omega is large, linear algebra, it becomes hard in some sense. Okay, so what are we really going to do? So if omega is 2.1, well, there's this result of Bauer and Strassen that says the determinant lower bound, right? That the n by n determinant n to the 2.1 circuit size to compute. Now, why is it interesting to look at the determinant? Well, let's rephrase this first. This says that linear size circuits can't compute the determinant. So what does that say linear size circuits can't do? They can't test if a matrix is singular or non-singular, right? That's what the determinant tells you. If it tells you if a matrix is invertible. So here, because the determinant is exactly what tells us about the rank of a matrix, we should think that singular matrices are going to look pseudo-random to small circuits. Now let's try to make this precise and see what happens. Okay, so we have a polynomial, and I want to understand, suppose, here's the idea of an algorithm I have. I take this polynomial, and I test it on every singular matrix. And if it comes up 0, I'm going to say, you know what, that 0 polynomial. And if it comes up non-zero, I definitely know it's non-zero. So what polynomials come up 0 on all the singular matrices? Well, you can show using some algebra that a polynomial vanishes at every singular matrix exactly when it's a multiple of the determinant. And not just a scalar multiple, but some polynomial multiple of the determinant. Okay? So what I'd like to say is that if omega is large, then small circuits shouldn't be able to compute not just the determinant, but all these multiples of the determinant. Right? Question is, can I show that if omega is large, do these polynomials inherit that lower bound? And then the second question you might be asking yourself is, wait a second, how do we evaluate at every singular matrix? Right? That's an infinitely large set. My algorithm can't do that. I don't have the time for that. So I first want to talk about this second question of, okay, wait, how do you actually evaluate at every singular matrix? And then we'll start understanding, how do we translate this lower bound to these other looking polynomials? Okay. So here's the generator that we're going to use. It takes as input two matrices. The first matrix is root n by root n minus 1, and the second matrix is the same size but transposed. The generator takes these two matrices, computes their product, and that's the output. And if you think about this, well, the image of this generator is exactly the set of singular matrices, right? And you can show that if a polynomial breaks this generator, if it vanishes on the output of this generator, then in fact, that polynomial must have been a multiple of the determinant. Okay, so instead of evaluating at all singular matrices, what I'm really going to do is we're going to use this generator that very clearly outputs a singular matrix, but it's really a collection of polynomials. Okay. So why do we care about these polynomials that break the generator? What we're going to do is we want to say that these polynomials are really hard to compute. So if I have a small circuit vanishes on the generator, well, it can't do anything interesting. So it must be the zero polynomial, right? That's what we want to say. But if you're looking carefully at the parameters here, there's a bit of an issue, which is there are more inputs than outputs to this generator, right? And the whole point of constructing a generator was to lower the number of variables, right? And this is definitely not doing that. Now, you could be a little bit more clever in how you parameterize your singular matrices, or we can change the rank value that we're going to look at. So instead of just trying to distinguish between singular and non-singular matrices, let's try to distinguish between low-rank matrices and high-rank matrices. So I'll replace the generator now. So now, again, the generator will take two matrices as input, but instead the first matrix is root n by r, and the second is r by root n, and it takes their product and outputs that. And you can see that this generator outputs matrices of rank at most r. Right? And now the question is, well, okay, the seed length has definitely improved, right? You should think of r as smaller than square root of n. The seed length has improved, so this could be useful for PIT. But now there's a problem of, well, we want to understand what polynomials could break this generator. What polynomials does this test fail for? And we do know something about what they look like. So one thing you could do is you could take a determinant of an r plus 1 by r plus 1 submatrix, take that determinant, multiply it by some other polynomial, that will vanish. You could add to that a multiple of another r plus 1 by r plus 1 minor, and so on. And we know actually these are exactly the polynomials that will break this generator. Okay? So the point is that we have some idea of what these polynomials look like. They're essentially sums of multiples of determinants where we're taking different submatrices. But I mean, there's a lot less structure here, right? In the singular versus non-singular case, we just had, a multiple of one determinant. Here, there's some weird addition going on, and it could be that one of these might actually be easy to compute, right? I might actually be able to break the generator with a small circuit because there could be some weird cancellation happening in these additions. Okay, but we at least know what we're fighting against to show that this generator is going to work. All right. So here's the roadmap. So what are we going to do? We have this lower bound on omega, and somehow, I haven't told you yet, but somehow we're going to show that any polynomial that breaks the generator, that requires some large circuit size, right? I need to do some work to break this generator. So then from there, this means that, I can set my rank value slightly less than the square root of n. I can show that if I set the rank to be n to like n to the 0.49, this generator will still hit linear sized circuits. And the proof of this arrow is really easy. So let's just look at that to understand why are we trying to prove this lower bound in the first place, right? So with this setting of parameters, any non-zero polynomial that breaks my generator requires a circuit of size like n to the 1.03 to compute, right? So if I'm testing a linear sized circuit and I see that it vanishes on the output of my generator, I couldn't started with a non-zero polynomial that vanished on my generator. I must zero polynomial. So that's why I want to. Okay. So if we have that lower bound, we show that this generator hits small circuits. And now you look and you say, this has seed length n to the 0.99. That's better than n. And now we use this general recipe that turns a generator into a PIT algorithm. And we get something that runs in time exponential in like n to the 0.99 times log n. All right, so this is the outline of the proof. And of course, I haven't told you about this very topmost arrow, which is how do you actually take the lower bound on omega and turn that into a lower bound on all the polynomials that break this generator. So let's zoom into that and see what's going on there. Okay, so here's the theorem that we want to prove, right? We want to prove something that looks hard. So you write the thing that you start with at the top, you write your conclusion at the bottom, and we're going to try to fill in the gaps. Okay, so we have this lower bound on omega. This is a lower bound on a multi-output function. It'll be a little nicer to work with a single output function. So what we're going to do is we're going to replace this with the trace of a product of three matrices. And there's this very nice work by Bauer and Strassen that says if you have low, it actually gives you a lower bound for this trace of matrix product. Okay. And now we still want to understand like what's going on with the polynomials that will vanish on this generator, right? Because those were very unstructured for those. But in some previous work together with Michael Forbes, we were able to understand these guys. And we showed that if you want to prove a lower bound on all the polynomials that vanish on this generator, it's enough to prove lower bounds for polynomials of a specific form. All right, so somehow we can assume a normal form on what these things look like. Before they were these sums of multiples of determinants, very complicated looking, very little structure. Now we can impose some additional structure. And what is that structure? Well, we can assume that our polynomial that we're trying to prove a lower bound for is a product of determinants. And in fact, it's a very special product of determinants. Every determinant in this product comes from an upper left submatrix, right? So I take, for some integer I take the first I rows and I columns of my matrix. And I take the determinant of that I. And these might appear with different powers, but I know there's at least one R by R determinant sitting in this product. Okay, so I want to prove that just this product of determinants is hard to compute. And then by some heavy machinery, you can actually get the thing we want to prove. So the main technical innovation in this work is really to prove this connection between a lower bound on this trace of matrix product and these products of determinants. All right, so we want to take trace of a product of three matrices, and we want to somehow express it as a determinant. All right, and I mean, we have to do more, we have to handle ours, but as a starting point, let's just express it as a determinant. Okay, so is the goal clear? Okay, great. So how are we going to write this trace as a determinant? So here's how this is just exactly what the trace of a product of three matrices is. I want to interpret it in terms of a graph. Okay, so this graph, it's going to be a four-partite graph. It has 4 layers with R vertices in each layer. And what I'm going to do is between the first and second layer, I'm going to draw an edge from I to j, and I'll put the variable yij on that edge. From the second to third layer, I'll draw an edge from the vertex j to vertex k and put the variable zijk on that edge. And then in the final layer, from layer 3 to layer 4, I'll put an edge from k to I, and I'll label it with the variable wki. All right, and now look at this path product of the edge labels. That's exactly one term in the trace, right? And if you sum over all possible paths that start at some vertex I in the first layer and end at some vertex I in the final layer, that will give you the trace. So instead of writing the trace as this sum of monomials, I'm going to write it in this graphical sense, right? It's a sum over paths in this graph that start and end at the same level of each layer. And we're going to, along that path, take the product of the edge labels. That's the trace. By doing this, we're getting some kind of graphical interpretation of the trace. Now I'll go on about a one-slide detour and tell you how the determinant relates to graphs. And then we'll come back and we'll try to piece these two interpretations together. Okay? So how does the determinant relate to graphs? So one piece of similarity that I want, I have a directed graph, and I want to, which are just vertex disjoint sets of cycles. These cycles should span all the vertices of the graph. So for example, here's one cycle cover in this graph. It's a set of vertex disjoint cycles. I allow for self loops, but we don't have to have them. And how is this related to the determinant? How are cycle covers related? Well, if I take the weighted adjacency matrix of this graph, so for the UV entry, I put the weight of the edge from U to V, and I take the determinant of this adjacency matrix. It's a sum over term. What is each term? Well, I'm going to take for every cycle cover in the graph, I'll get the product of the edge labels in that cycle cover. Cycles are in that cycle cover, right? Let's not worry too much about the sign term, but this is somehow counting all of your cycle covers and taking the sum over the products of their edge labels. And one way to see this is, well, every term in the determinant corresponds to a permutation, and you can decompose permutations into disjoint cycles. Right? And if you think about what is a permutation on a graph, I mean, it's this set of cycles in the graph. Right? So going back to the trace, we have a graph, we have an interpretation of the trace on this graph, and we have some interpretation of the determinant in terms of graphs. But the problem is, well, the trace is talking about paths that start in the first layer and end in the last layer, and the determinant is talking about cycle covers, and this graph is very acyclic. Right? So we need to put some cycles in here and somehow hope that those cycle covers will correspond to these paths that start and end at the same level of the graph. Right? So how are we going to do that? Okay, so let's just make the graph bigger so we can see what's going on. Okay, so here's the natural thing to try and do. For every I, I'm going to add an edge going backwards from vertex I in the final layer to vertex I in the first layer. Now this takes this path from I to I and it turns it into a cycle. Right? You can see the cycle here in the picture, but it's not, that path hasn't become a cycle cover yet because I need to put cycles on all the other vertices. So the natural thing to do is let's put self loops on every single vertex. And now for every path that goes from I to I have a corresponding cycle cover. And the weight of that cycle cover is it's this one term from the trace. Right? So we're getting there, but there's a problem that we've introduced cycles that we don't want to count. Right? And one example would be a cycle that looks like this, where we start at vertex I, but we end at some other vertex. We loop around, we take another path, we go back down to I, and then we take this backwards edge. Right? That gives us some degree 6 term in the determinant, and we really don't want that. You could also take disjoint cycles that corresponded to these paths in the trace, right? So we're kind of getting there, but we've got these erroneous terms that we somehow want to suppress in an interesting way. So here's what we're going to do. Our goal covers that use at most one edge that goes backwards. Right? If I'm using one edge going back, then I have to look like the cycle cover that's drawn here. And if I use more than that, well, I'm definitely not corresponding to something from the trace. And if I use no backwards edges, I'm the all ones cycle cover. Okay, so what are we going to do? So let's add on each of these backwards edges a new variable epsilon. And you can either think of epsilon as a variable or you can think of it as a small real number. Now, here's what we can do. We can take the determinant of the adjacency matrix of this graph, this weighted sum of cycle covers, and we can write it as a polynomial. Now, what is the coefficient of epsilon to the I here? What does that count? Well, how would I get I powers of epsilon? I would use I backwards edges. Right? So here I get exactly what I want. I can somehow control or at least pull out, how many cycle covers used 0 edges going backwards. 1, 2, 3, and so on. And so what we can do is we can actually write down the determinant of the adjacency matrix of this graph. Well, If I use no backwards edges, I'm using all the self loops, I get a 1. If I use one backwards edge, I get the trace. And if I use more than one, I don't care. Epsilon is small, you should think of that as an error. Now I haven't quite, remember, our goal was to write the trace as a determinant. And we didn't quite do that. We kind of did, but not yet. Oh no, you can take the trace, you can get the trace by taking this determinant, subtract 1, divide through by epsilon, and take a limit. Right? And I never promised that I was going to compute this exactly. And it turns out that in the details, it's fine to compute this in the limit as opposed to computing it exactly. And in fact, using this limiting form of computation, this is very, very crucial to what we're doing here. I don't know how to do this without the limit. So that's how we can write the trace as a determinant of some matrix, right? And so what were we trying? Let's encapsulate this by saying, what is the actual matrix we wrote down here? Right? So if you write this matrix M, this block diagonal matrix where you've got identities on the main diagonal, you've got these YZW matrices immediately above the diagonal, and this epsilon times identity in the bottom left corner. Its determinant is this 1 plus epsilon times trace plus lower order terms. Okay, and so we saw how to get a trace out of a single determinant. But if you remember, why are we doing this? Why are we, messing around with all these traces and determinants and trying to be really careful about this? Well, the reason for this is we wanted to narrow, right? We wanted to somehow say that if I have a lower bound on the trace, then I get a lower bound for all these products of determinants, right? And I showed you like how to do this for one determinant. But I didn't show you how to do this. The algebra can actually do this for any kind of product of determinants that you want. The lower bound will still work. And it somehow uses the fact that because we have this 1 plus epsilon here, you could think, well, what happens when I take a power of this? What happens when I square this? Well, the epsilon, the linear term in epsilon just becomes 2 times the trace. If I take a third power of this, the linear term in epsilon becomes 3 times the trace. So that should convince you that for powers of determinant, that's fine. If I take determinants of small enough upper left submatrices, that's also fine, because eventually this becomes upper triangular. And then there's some nonsense in the middle going on, and you can work that out, but I don't want to, we don't need to go through all the calculations here. But this works. So what did we do? Why were we doing this? We had a lower bound on omega, and we wanted to say that that lower bound extends to all polynomials that break this generator. And we needed to fill in this gap. We needed to somehow go from a trace to products of determinants. Okay, so we did that. Now going back, why did we do that? The reason we did that is we had this plan that if I prove a lower bound on omega, I can de-randomize polynomial identity testing. And the key missing step was I needed to prove that this lower bound extends to all these polynomials that might break our generator. So we did that. So that's the proof. And up to futzing around with some of the arithmetic, this is more or less the whole proof. So here's what I want you to take away, because I know you're not, I don't expect you to remember all the algebra in about 2 or 3 hours after you've had lunch. You've maybe watched some of the World Cup. So what should you remember? If omega is 2.1, if it's not 2, low rank matrices look pseudo-random to small circuits. That's the message here. And of course, in this work, we're actually doing a very precise formal version of this, but this is the takeaway. If you have a lower bound on omega, low rank matrices look pseudo-random to small circuits. Okay, so, right, so that's all I want to say. So let me end with some questions that are left open by this work, some other directions to explore. So one thing I never mentioned is the dependence on the underlying field. And here we really need to be working over a field of characteristic 0, because I want to divide by every natural number you could throw at me. In positive characteristic, the proof breaks. I think it would be interesting to do this or get some analogous result in positive characteristic. The second question is, well, could do strapping on the PIT? We have this lower bound on omega. We get a nice algorithm for PIT, but its running time is kind of weak. Maybe you could do some fancy recursion or some kind of interesting construction on top of this. and improve the algorithm even more? Or dually, could you magnify the lower bounds? Right? You start with a very weak lower bound, but for a very specific problem with special structure to it, you come this construction and get a stronger lower bound, but for a different problem, you could use standard hardness versus randomness tools to de-randomize PIT. And the final question, which is mostly for the experts in the audience, there's an unconditional result sitting in here too, which is we know the border rank is at least n squared. And so you get some kind of unconditional for circuits of like sublinear multiplication gates, which turns out to be interesting. And this comes in a logarithmic factor of you could hope for having a new circuit lower bound. And there's this roughly n log n circuit lower bound due to Bauer and Strassen, which is the best thing we know, and it's been the best thing we know for 40 years. Can we somehow get some insight from their lower bound and design in interesting circuits? So that's all I wanted to say. Thank you all so much for your time. Yeah.
You probably covered this already with your problem, but I was just wondering what's the motivation for
I think, well, I mean, there's this broader question, right, of how much power does randomness fundamentally buy you in computation, right? That, I mean, you know, as far as applications, maybe you're fine with a randomized algorithm. Maybe you really want to know. Maybe you're doing some kind of program checking, right? And you really, really want to know that the code you wrote is like actually correct, not 99% sure it's correct, but 100% sure. Then you might want to get rid of the randomness. But I mean, more broadly, I'm interested in it because I want to know, like, do random bits really buy us more power than polynomial time, right? And it would be nice to understand. I mean, I would really love to see an answer to that question in like my lifetime. So yeah.
Okay, we have another question from the audience.
Yeah.
So, very nice and interesting proof. Is there any hope to prove a partial converse to your result?
Prove a partial converse.
Yeah, that if you had an efficient PIT for these circuits, then you, so like the partial converse, right? So you prove that, okay, omega implies something and you want the other way around.
Oh,
That you can prove a lower bound omega through
de-randomization.
right.
I think not, because if you could prove that, that would kind of be that would say that either omega is 2 or you can de-randomize PIT, but not both, which would be surprising, right? So yeah.
It's like maybe the question is more like the question that is being asked is like if you, in a sense, like do a fine-grained complexity sense, right?
Mm-hmm.
There's this problem, okay, PIT for these types of circuits,
Mm-hmm.
and then if you get kind of better algorithms there that can go all the way down to matrix multiplication, right? Is it similar to this kind of
I see.
things, right? That like
Yeah.
this exponential time hypothesis breaks, then okay, all these kind of cubic algorithms, they are optimal, right?
Yeah, I see. I don't know. I haven't thought about this, but that's a really interesting question.
Yeah, I agree.
Yeah.
Any more questions? Okay, so if we have no more, thank Robert again. And I guess, can you guys hear me over Zoom? Or maybe Robert, you can say.
I don't know.